In the realm of marine engineering, achieving optimal performance for planing boat hulls is a constant pursuit. These hulls, characterized by their ability to rise up and glide on the water surface at high speeds, present unique design challenges. Understanding their behavior under various conditions is crucial for maximizing speed, efficiency, and stability. This is where the power of computational fluid dynamics, or CFD, simulations comes into play. CFD provides naval architects and engineers with a virtual testing ground to study the complex interactions between a boat hull and the surrounding water. By simulating the flow of water around a hull, CFD can accurately predict crucial performance parameters such as drag, trim, angle, and sinkage. This information is invaluable for optimizing hull design, reducing drag, and improving overall performance. ANSYS Fluent, a leading CFD software package, offers a comprehensive suite of tools for simulating planing boat hulls with a high degree of accuracy. Its dynamic mesh. 6 degrees of freedom capabilities allow engineers to model the complex motions of a boat as it moves through the water, providing realistic and insightful simulations. This guide will serve as your comprehensive roadmap to mastering planing boat hull simulations using ANSYS Fluent. We will delve into the intricacies of setting up and running these simulations, empowering you with the knowledge to confidently analyze and optimize hull designs. Whether you are a seasoned CFD practitioner or new to the field, this guide will equip you with the tools and understanding to harness the power of ANSYS Fluent for planing boat hull simulations. This guide focuses on a specific simulation scenario, a transient 2-degree of freedom analysis of a generic planing speedboat. Our primary objective is to accurately predict 3 key performance indicators: drag, trim angle, and sinkage. Drag, the resistance force exerted by water on the hull, plays a significant role in determining a boat's speed and fuel efficiency. Trim angle, the angle between the hull's keel line and the horizontal water surface, affects stability and resistance. Sinkage, the vertical displacement of the hull into the water, influences both drag and trim. To achieve accurate predictions of these parameters, we will employ a combination of advanced techniques within ANSYS Fluent. The open channel volume of fluid method will be used to model the complex interaction between the air and water phases. Fluent's 6 degrees of freedom solver will enable us to accurately capture the boat's motion in response to hydrodynamic forces. The moving deforming mesh technique will allow the simulation mesh to dynamically adapt to the boat's movement, ensuring accurate representation of the flow field throughout the simulation. Throughout this guide, we will provide a step-by-step breakdown of the entire simulation process, from geometry and mesh creation to setting up simulation parameters and analyzing the results. We will cover essential aspects such as defining boundary conditions, selecting appropriate solution methods, and ensuring simulation stability. By the end of this guide, you will possess a solid understanding of the fundamental principles and practical techniques required to successfully simulate planing boat hulls using ANSYS Fluent. Imagine a massive water tank, carefully controlled for calmness and equipped with sophisticated sensors to track every movement of a boat placed within it. This is the essence of what we aim to create virtually using ANSYS Fluent, a controlled environment to study the intricate behavior of a planing boat hull. This virtual test basin allows us to replicate real-world conditions and observe the hull's performance without the need for expensive and time-consuming physical testing. Our simulation focuses on a simplified yet representative scenario. We start with the boat at rest, partially submerged in the water. This initial state allows us to observe the initial forces acting on the hull and how it responds to these forces as it begins to move. The virtual test basin is large enough to accommodate the boat's motion and the wave patterns it generates without introducing unwanted boundary effects. The size and shape of this virtual test basin are crucial considerations. The domain, as it's technically called, needs to be large enough to avoid reflections of waves from the boundaries back onto the hull, which could interfere with the accuracy of our results. We also need to ensure that the water depth is sufficient to simulate the boat's behavior realistically. By carefully defining the dimensions and boundary conditions of our virtual test basin, we create a controlled and isolated environment where the only forces acting on the boat are those we want to study, hydrodynamic forces from the water and gravity. This controlled setting allows us to isolate the effects of different hull designs and operating conditions, leading to a deeper understanding of planing hull performance. Our simulation doesn't just capture a snapshot in time, it unfolds dynamically, mimicking the boat's transition from a stationary position to a state of planing. This transition is a critical aspect of planing hull performance, characterized by a complex interplay of forces and changes in the hull's attitude. Initially, the hull experiences a higher resistance as it pushes through the water. As the boat gains speed, the hull starts to lift out of the water, reducing the wetted surface area and consequently the drag. This transition phase is where the dynamic meshing capabilities of ANSYS Fluent truly shine. As the boat moves and changes its orientation, the mesh surrounding it deforms and adapts in real time. This ensures that the computational grid accurately captures the flow field around the hull throughout the entire simulation, even as the hull's position and the shape of the water surface change dramatically. Capturing this transition accurately is crucial for understanding the transient forces acting on the hull and how they affect its stability. The simulation allows us to observe how the trim angle changes as the boat accelerates and how this affects the wetted surface area and the overall resistance. This information is invaluable for designing hulls that can transition to planing smoothly and efficiently. By studying the transient behavior of the hull, we gain insights that would be difficult, if not impossible, to obtain through experimental methods alone. This detailed understanding of the transition phase is key to optimizing hull designs for faster acceleration, improved stability, and reduced fuel consumption. Section 3. Visualizing the flow insights from wave patterns. One of the most captivating aspects of CFD simulations is the ability to visualize the invisible, the flow of water around the hull. ANSYS Fluent allows us to generate detailed visualizations of the flow field, providing valuable insights into the hydrodynamic phenomena at play. Of particular interest are the wave patterns generated by the boat as it moves through the water. These wave patterns are not merely aesthetically pleasing, they hold valuable information about the hull's performance. The shape and size of the waves are directly related to the energy dissipated by the hull as it moves through the water. By analyzing these patterns, we can gain insights into the hull's resistance and identify areas where design modifications could lead to improved efficiency. ANSYS Fluent provides a range of tools to visualize these wave patterns. We can create animations showing the evolution of the wave field over time, providing a dynamic view of how the hull interacts with the water. We can also generate contour plots of pressure and velocity on the hull surface and in the surrounding water, highlighting areas of high pressure and flow separation. These visualizations are not just for show, they are powerful diagnostic tools that allow us to understand the complex flow phenomena affecting hull performance. By carefully studying these visualizations, we can identify areas of high drag, optimize hull shape for reduced wave-making resistance, and ultimately design more efficient and higher performing planing boat hulls. Section 1. A closer look at the hull dimensions and design. For this simulation, we're employing a generic boat hull meticulously crafted to serve as a representative model for our exploration of planing dynamics. While not a replica of a specific commercial design, this generic hull allows us to focus on the fundamental principles of planing without being bogged down by the intricacies of a particular boat. Think of it as a blank canvas, ready to be analyzed and understood as we delve into the world of CFD simulations. Our hull measures 5 meters in length, a size that strikes a balance between computational feasibility and representing the characteristics of a small to medium-sized planing boat. Its weight, a crucial parameter influencing its behavior, is set at 500 kilograms. However, to optimize computational resources, we'll be leveraging the inherent symmetry of the hull. By focusing on one half of the hull and applying symmetry boundary conditions, We effectively halve the computational domain, reducing simulation time without compromising the accuracy of our results. The hull's design, while simplified, incorporates the essential features that dictate planing behavior. The shape of the bottom, known as the hull form, plays a crucial role in determining how the boat interacts with the water as it accelerates. The dead rise angle, the angle between the horizontal plane and the hull's bottom surface, influences the hull's stability and its ability to handle rough water. While we won't be delving into the specifics of hull form optimization in this guide, understanding the influence of these design parameters is crucial for appreciating the nuances of planing hull performance. By starting with a generic hull, we establish a common ground for understanding the fundamental principles of planing. This foundation will serve us well as we progress to more complex simulations involving real-world hull designs and operating conditions. Section 2, Defining the Boundaries, Creating our Virtual Water World. With our hull defined, we shift our attention to creating the virtual environment in which it will be simulated, our computational domain. This domain, representing a section of water, needs to be large enough to accommodate the boat's motion and the wave patterns it generates, while minimizing unwanted boundary effects that could skew our results. The total length of our domain is approximately 4 times the length of our boat, extending 2 boat lengths upstream and 1 boat length downstream. This ensures that the waves generated by the hull have sufficient space to propagate naturally without reflecting off the boundaries and interfering with the flow around the boat. The upstream region provides a sufficient distance for the flow to develop naturally before encountering the hull, while the downstream region allows for the observation of the weight generated by the boat. The depth and width of the domain are equally important considerations. The water depth needs to be sufficient to allow for the boat's vertical motion during planing without the hull bottom coming too close to the domain boundary. Similarly, the width of the domain, while influenced by computational constraints, should be large enough to prevent the sides of the domain from affecting the flow around the hull. Defining these boundaries appropriately is crucial for creating a realistic and isolated simulation environment. By minimizing boundary effects, we ensure that the forces acting on the hull are predominantly those arising from its interaction with the water and gravity, allowing us to isolate and study the fundamental principles of planing. Section 3, Symmetry, Leveraging Efficiency in Simulation Setup. Computational efficiency is a paramount concern in CFD simulations, especially those involving complex geometries and dynamic motions like our planing boat. To streamline our simulation and reduce computational cost without sacrificing accuracy, we exploit a powerful tool, Symmetry. Our boat hull, like many marine vessels, exhibits geometric symmetry along its center line. This means that one half of the hull is a mirror image of the other. By taking advantage of this symmetry, we can effectively halve the size of our computational domain. Instead of simulating the entire hull, we focus on only one half, applying a symmetry boundary condition along the center line. This boundary condition ensures that the flow field on one side of the symmetry plane is mirrored on the other side, effectively representing the behavior of the full hull while significantly reducing the number of computational cells required. This reduction in domain size translates directly into faster simulation times. With fewer cells to solve for, the computational cost decreases, allowing us to achieve results more quickly or explore a wider range of parameters within a given time frame. This efficiency gain is particularly valuable in iterative design processes where multiple simulations are often required. Exploiting symmetry is a common and effective technique in CFD simulations, particularly in marine applications where many vessels exhibit geometric symmetry. By leveraging this inherent property of our model, we optimize our simulation setup for efficiency without compromising the accuracy of our results, paving the way for a faster and more efficient exploration of planing hull performance. Section 1. Crafting the digital fabric meshing for accuracy. In the world of computer simulations, representing a continuous, flowing substance like water requires a bit of digital artistry. We can't simply tell the computer there's water here. We need to break down the space around our boat hull into a manageable grid of smaller volumes, our computational mesh. Imagine this mesh as a finely woven fabric draped over and around the hull, dividing the fluid domain into millions of tiny cells. Each cell in this mesh acts like a mini laboratory where the computer solves equations governing fluid flow. The size and shape of these cells directly influence the accuracy and stability of our simulation. Too large and we risk oversimplifying the flow, missing crucial details. Too small and the computational cost skyrockets, potentially bogging down even powerful computers. For our planing boat hull simulation, we strive for a balance between accuracy and efficiency. We employ a combination of different cell shapes to achieve this balance. Near the hull surface, where flow gradients are steepest, we use tetrahedral cells. These pyramid-shaped cells excel at capturing complex geometries and flow features. Further away from the hull, where flow is smoother, we transition to hexahedral cells. These cube-shaped cells are computationally less demanding and well-suited for regions with less flow variation. This hybrid meshing approach allows us to concentrate computational effort where it matters most, near the hull, where accuracy is paramount, while maintaining overall efficiency. The transition between these different cell types is carefully managed to ensure a smooth flow of information within the simulation, preventing numerical artifacts that could compromise our results. Section 2. Balancing act mesh density and computational cost. Meshing is not a one-size-fits-all endeavor. The density of our mesh, the number of cells packed into a given volume, plays a crucial role in determining the accuracy and computational cost of our simulation. A denser mesh with smaller cells generally leads to higher accuracy by better resolving flow details. However, this increase in accuracy comes at a price: computational time. For our boat hull simulation, we aim for a mesh that is fine enough to capture the essential flow features while remaining computationally manageable. Our mesh consists of approximately 1.6 million cells, a number that reflects a compromise between accuracy and efficiency. The majority of these cells, around 1.3 million, are concentrated near the boat hull, where flow gradients are steepest and accurate resolution is crucial. The remaining 0.3 million cells make up the outer domain, where a coarser mesh suffices. This non-uniform mesh density allows us to optimize computational resources. We allocate more cells to regions where flow details are critical, ensuring accurate capture of phenomena like flow separation and turbulence generation near the hull. In regions where flow is smoother, we can afford to use a coarser mesh, reducing the overall cell count and computational cost without sacrificing the overall accuracy of our results. Finding the right balance between mesh density and computational cost is often an iterative process. It involves running simulations with different mesh resolutions, comparing results, and assessing the trade-off between accuracy and computational time. Experience and a good understanding of the flow physics involved are invaluable in guiding this mesh refinement process. One of the unique challenges in simulating planing boat hulls lies in accurately capturing the behavior of the water surface. Unlike simulations where the water surface remains relatively flat, our planing hull generates waves, creating a dynamic interface between water and air that needs to be carefully managed within our mesh. This is where specialized meshing techniques come into play. To ensure accurate representation of this free surface, we employ a technique called prism layer meshing. Imagine attaching a thin layer of perfectly stacked rectangular boxes to the hull surface. These boxes, our prism layers, follow the contours of the hull, creating a high-quality mesh that accurately captures the curvature of the hull and the dynamic water surface. These prism layers serve a critical purpose. They provide a structured, high aspect ratio mesh in the immediate vicinity of the hull, improving the accuracy of pressure and shear stress predictions, crucial parameters for calculating drag and understanding hull performance. The number of prism layers used is a balancing act. Too few and we risk compromising accuracy. Too many and we add unnecessary computational cost. In addition to prism layers, we employ a technique called body of influence mesh refinement. This technique allows us to selectively refine the mesh in regions where we anticipate high flow gradients, such as near the waterline, where the hull transitions from being submerged to planing. By concentrating cells in these critical areas, we ensure accurate capture of the complex flow phenomena occurring as the hull moves through the water. These specialized meshing techniques are essential for accurately capturing the dynamic behavior of the water surface in our planing boat hull simulation. By carefully managing the mesh in these critical regions, we ensure that our simulation accurately represents the complex interplay between the hull, the water, and the air, leading to reliable predictions of hull performance. With our geometry and mesh in place, we turn our attention to the heart of our simulation, defining the physical laws and models that will govern the behavior of our virtual water and boat. This is where we transform our digital creation from a static representation into a dynamic system mimicking the real-world physics of fluid flow. Our simulation centers on the interaction between two fluids, air and water. To accurately capture this interaction, we employ the volume of fluid, VOF method, a powerful technique for modeling two-phase flows with a clearly defined interface. Imagine the VOF method as a way of tracking which parts of our computational mesh are occupied by water and which by air, allowing us to simulate the wave formation and hull-water interaction realistically. The open channel flow option within the VOF model further refines our simulation by accounting for the presence of a free surface, the interface between water and air. This option is crucial for accurately capturing the wave patterns generated by the boat and their influence on hull resistance. To ensure a crisp representation of the water surface, we opt for sharp interface modeling, minimizing numerical diffusion that could blur the boundary between the two fluids. Finally, no simulation of fluid flow is complete without addressing turbulence, the chaotic swirling motions that dominate fluid behavior at high speeds and near boundaries. We employ the K-omega SST turbulence model, a widely used and robust model known for its accuracy in predicting flow separation and turbulence generation near walls, crucial aspects of planing hull performance. In the real world, a boat doesn't exist in isolation. It interacts with the surrounding air and water, influenced by forces and conditions at its boundaries. In our simulation, we need to define these boundaries carefully, translating real-world conditions into numerical constraints that guide the flow of information within our computational domain. Our outer boundaries, the virtual walls of our water tank, are defined as symmetry planes, with the exception of the inlet, outlet, and boat hull. This symmetry condition ensures that the flow behaves as if it were mirrored across these boundaries, minimizing edge effects that could influence our results. Think of it as creating an infinitely repeating pattern of our simulation domain, eliminating the influence of artificial boundaries. At the inlet, where water enters our virtual tank, we specify a fixed velocity and volume fraction. This defines the speed and depth of the incoming flow, essentially mimicking the conditions of a controlled towing tank experiment. The outlet, where water exits the domain, is defined as a pressure outlet. Here we specify a fixed pressure, allowing water to flow out naturally while maintaining a stable flow field within the domain. Finally, the interface between the boat hull and the water requires special attention. We define this boundary as a wall, specifying the no-slip condition, which dictates that the fluid velocity at the hull surface is zero, a standard assumption in fluid dynamics. We also define the contact angle, the angle at which the water surface meets the hull, a parameter that influences the wetted surface area and drag. Section 3, breathing life into the simulation, initializing the flow. With our physical models and boundary conditions in place, we're almost ready to set our simulation in motion. However, before we hit the start button, we need to provide ANSYS Fluent with an initial guess for the flow field, a starting point from which the solver can begin its calculations. This initialization step is crucial for ensuring that our simulation starts smoothly and converges towards a physically realistic solution. For our planing boat hull simulation, we opt for a standard initialization based on the inlet conditions. This means that the solver will assume an initial flow field where the water surface is perfectly flat and the velocity is uniform across the inlet, gradually transitioning to a more complex flow pattern as the simulation progresses. This initialization method is generally suitable for cases where the initial flow field is not well defined or where we expect the flow to evolve significantly during the simulation. The open channel flow method we selected earlier plays a crucial role in this initialization process. It ensures that the initial water level and velocity profile are consistent with the specified inlet conditions and the gravitational forces acting on the fluid. This consistency is essential for preventing spurious pressure waves or unrealistic flow patterns from developing during the initial stages of the simulation. Once initialized, our simulation is ready to capture the dynamic interplay between the boat hull and the surrounding water. As the solver iterates through time, it will update the flow field based on the defined physical models and boundary conditions, gradually converging towards a solution that reflects the complex hydrodynamic phenomena at play as our virtual boat begins to plane. Section 1. Enabling motion breathing life into the hull. Up to this point, our simulated boat hull has been a static entity, a digital sculpture awaiting its moment to interact with the virtual water. Now we activate the dynamic mesh capabilities of ANSYS Fluent, breathing life into our hull and transforming it from a stationary object into a dynamic participant in our simulated world. This transition from static to dynamic requires a fundamental shift in how the software perceives and handles the hull within the flow field. First, we activate the diffusion-based smoothing option. Think of this as a digital lubricant that allows the mesh to deform smoothly as the hull moves through it. Without this smoothing, the mesh could become tangled or distorted, leading to numerical instabilities and inaccurate results. The diffusion parameter, set to approximately 1, controls the extent of this smoothing, a delicate balance between allowing for significant deformation while maintaining mesh integrity. Next, we activate the 6DOF solver, the heart of our dynamic mesh setup. This solver, short for 6 degrees of freedom, empowers our hull to move and rotate freely in response to the forces acting upon it. Imagine a ship captain at the helm, free to steer the boat in any direction. The 6DOF solver grants our virtual hull this same freedom, allowing it to heave, pitch, roll, yaw, sway, and surge in response to the hydrodynamic forces it encounters. Finally, we enable the right motion history option. This seemingly mundane setting is our virtual black box, recording the hull's every move and rotation throughout the simulation. This motion history becomes a valuable tool for post-processing, allowing us to analyze the boat's trajectory, trim angle, and sinkage over time, and gain insights into its dynamic behavior. Section 2. Guiding the movement user-defined functions for realistic motion. While the 6DOF solver grants our hull freedom of movement, it's crucial to ensure this movement adheres to the laws of physics and reflects the characteristics of a real boat. This is where user-defined functions, or UDFs, come into play. UDFs are snippets of custom code that allow us to inject specific behaviors and constraints into our simulation, bridging the gap between the generic capabilities of the software and the unique requirements of our model. In our case, the UDF acts as the invisible hand guiding the hull's motion. We define 3 key parameters within this UDF: mass, moment of inertia, and allowed degrees of freedom. The mass, set at 250 kilograms due to our symmetrical setup, dictates how the hull responds to forces. A heavier hull will accelerate slower and be less susceptible to the influence of waves, while a lighter hull will be more agile but potentially less stable. The moment of inertia, a measure of an object's resistance to rotational acceleration, is equally crucial. This parameter, calculated based on the hull's shape and mass distribution, determines how easily the boat pitches, rolls, and yaws in response to forces. A hull with a high moment of inertia will be more resistant to these rotations, while one with a lower moment of inertia will be more responsive, but potentially less stable. Finally, we define the allowed degrees of freedom. In our 2 degrees of freedom simulation, we restrict the hull's movement to heave, which is vertical motion, and pitch, which is rotation around the transverse axis, mimicking the behavior of a boat moving in calm water without the influence of steering or external disturbances. Section 3. zones of transformation defining how the mesh responds. With our hull imbued with the ability to move realistically, we turn our attention to the surrounding mesh. The mesh, our digital representation of the water, needs to adapt dynamically to the hull's motion, maintaining its integrity and accuracy as the boat carves its path through the virtual fluid. This dynamic adaptation is achieved by defining specific zones within the mesh and assigning them distinct behaviors. First, we define the interface surfaces, the boundaries between the tetrahedral mesh surrounding the hull and the hexahedral mesh in the outer domain as deforming zones. These zones act like flexible membranes, stretching and compressing as the hull moves, ensuring a smooth transition between the different mesh regions. The symmetry plane, dividing our computational domain in half, is also designated as a deforming zone, mirroring the mesh deformation on one side to the other, and maintaining symmetry throughout the simulation. Next, we define the boat hull itself as a rigid body zone with the 6 degrees of freedom option activated. This designation tells ANSYS Fluent that the hull is a solid object that moves as a single unit, its motion governed by the 6 degrees of freedom solver and the parameters defined in our user-defined functions. The mesh within this zone moves rigidly with the hull, ensuring that the boundary layer, the thin region of fluid immediately adjacent to the hull surface, is accurately captured. Finally, we define the prism layer zone, our meticulously crafted mesh region hugging the hull surface. Similarly to the boat hull zone, but with the 6 degrees of freedom option set to passive. This designation ensures that the prism layers move with the hull, maintaining their position relative to the hull surface and preserving the accuracy of our boundary layer resolution. By carefully defining these zones and their behaviors, we transform our mesh from a static grid into a dynamic, responsive entity that can accurately capture the complex fluid structure interaction as our virtual boat moves through the water. Action 1, pressure-velocity coupling, a delicate dance for stability. In the realm of fluid dynamics, pressure and velocity are inextricably linked, two partners in an intricate dance that governs the flow of liquids and gases. In our CFD simulation, accurately capturing this dance is crucial for achieving stability and obtaining physically meaningful results. This is where the concept of pressure-velocity coupling comes into play, a numerical technique that dictates how ANSYS Fluent handles the interdependence of these two fundamental flow variables. For our planning boat hull simulation, we employ the coupled pressure-velocity coupling scheme. This scheme, as its name suggests, solves for pressure and velocity simultaneously within each iteration of the solver. Imagine two dancers moving in perfect synchrony, their steps influencing each other in real time. Similarly, the coupled scheme ensures that pressure and velocity fields evolve together, maintaining a consistent and balanced flow field throughout the simulation. This coupled approach is particularly well suited for transient simulations like ours, where the flow field undergoes significant changes over time. The simultaneous solution of pressure and velocity helps to dampen numerical oscillations that can arise in transient flows, leading to a more stable and robust simulation. It's like having a skilled choreographer guiding our dancers, ensuring their movements remain harmonious even as the tempo picks up. The coupled scheme, while computationally more demanding than segregated schemes that solve for pressure and velocity separately, often leads to faster convergence, especially in cases involving complex geometries or free surfaces. This efficiency gain stems from the scheme's ability to propagate information about pressure and velocity changes throughout the domain more effectively, leading to a more rapid convergence towards a stable and accurate solution. Section 2, Spatial Discretization, translating physics into numerical language. At the heart of any CFD simulation lies a fundamental challenge, translating the continuous, flowing nature of fluids into a discrete language that computers can understand and solve. This translation process, known as spatial discretization, involves transforming the governing equations of fluid flow, partial differential equations, into a system of algebraic equations that can be solved numerically within each cell of our computational mesh. ANSYS Fluent offers a variety of spatial discretization schemes, each with its own strengths and weaknesses depending on the specific flow characteristics being simulated. For our planing boat hull simulation, we carefully select schemes that balance accuracy, stability, and computational cost. For the gradient terms in our equations, representing spatial variations in flow variables, we employ the least squares cell-based scheme. This scheme, while computationally less demanding than some higher-order schemes, offers a good compromise between accuracy and stability for a wide range of flow problems. It's like using a reliable compass to navigate our way through the mesh, ensuring that our calculations of flow gradients are consistent and accurate. For pressure, we opt for the Presto scheme, short for pressure staggering option. This scheme excels at handling pressure-velocity coupling near boundaries and interfaces, crucial for accurately capturing the pressure distribution on our hull surface and the behavior of the free surface. Imagine this scheme as a skilled artisan, carefully shaping the pressure field to ensure a smooth and physically realistic flow around our boat hull. Section 3, Taming the Transient's Time Steps and Convergence Control. Transient simulations, unlike their steady-state counterparts, capture the evolution of flow over time, like a high-speed camera recording the intricate details of a breaking wave. This temporal resolution comes at a cost, requiring careful control of the time step, the increment in time over which the solver advances the solution, and robust convergence criteria to ensure accuracy and stability. For our planing boat hull simulation, we adopt a ramping approach to time step selection. We begin with a relatively small time step, 0.0025 seconds, and a limited number of iterations per time step, 10 iterations per time step. This cautious approach allows the simulation to stabilize during the initial stages when the flow field undergoes rapid changes as the boat begins to move. Think of it as gently easing our virtual boat into the water, allowing the flow to adjust gradually. As the simulation progresses and the flow field becomes more established, we gradually increase the time step and the number of iterations per time step to 20 iterations per time step. This ramp-up in temporal resolution allows us to capture the later stages of the simulation, where the boat approaches a steady planing state, with greater efficiency without compromising accuracy. It's like shifting gears in a car, gradually increasing speed as the road ahead becomes smoother. To monitor convergence within each time step, we track residuals, measures of the imbalance in the governing equations. These residuals, like tiny error signals, indicate how well our numerical solution satisfies the underlying physics. We set strict convergence criteria for these residuals, ensuring that they decrease by several orders of magnitude within each time step. This meticulous approach guarantees that our solution is not only stable but also accurately represents the physical processes at play. Throughout the simulation, we remain vigilant, monitoring residuals and adjusting time step size and convergence criteria as needed. This adaptive approach, like a skilled captain adjusting course based on sea conditions, ensures a smooth and successful voyage through the challenging waters of transient CFD simulation. Section 1, Keeping Watch. Monitoring for insights and stability. Imagine peering through a window into a bustling laboratory, observing an experiment unfold in real time. This is the essence of monitoring in CFD simulations, keeping a watchful eye on key parameters as our virtual experiment progresses. These parameters, like gauges and sensors in a physical test, provide invaluable insights into the behavior of our simulation, alerting us to potential issues and guiding us towards a stable and accurate solution. In our planing boat hull simulation, we set up several monitors to track crucial aspects of the flow and the boat's motion. One of our primary interests is drag, the resistance force exerted by the water on the hull. We define a drag monitor aligned with the direction of flow, which continuously calculates and records the drag force acting on the boat throughout the simulation. This monitor provides us with a real-time view of how drag evolves as the boat accelerates and transitions to a planing state. To delve deeper into the pressure distribution around the hull, we set up a surface monitor that integrates pressure over the entire hull surface. This integrated pressure value, plotted for each iteration of the solver, provides a global measure of the forces acting on the hull and how they change over time. Fluctuations in this pressure integral can indicate potential instabilities in the simulation, prompting us to investigate further and adjust parameters as needed. Finally, to keep track of the boat's motion, we monitor the vertical position of a specific point on the hull, such as the bow or stern. This monitor, plotting the z-coordinate of this point over time, provides a clear visualization of the boat's heave motion, its vertical displacement as it transitions from a submerged state to planing. By observing this motion, we can assess the stability of the boat and how effectively it rises out of the water. Section 2. Setting the starting line, initializing the flow. Imagine an athlete poised at the starting line, muscles tensed, awaiting the signal to unleash their energy. Similarly, our CFD simulation requires an initial state, a starting point from which the fluid flow and the boat's motion can evolve realistically. This initialization step, while seemingly simple, plays a crucial role in ensuring that our simulation starts smoothly and converges towards a physically meaningful solution. For our planing boat hull simulation, we opt for a standard initialization computed from the inlet. This initialization method assumes an initially undisturbed flow field with a flat water surface and a uniform velocity profile at the inlet, mimicking the conditions in a towing tank before a test begins. This initial state provides a clean slate from which the flow can develop naturally as the boat starts to move. The open channel flow option we activated earlier plays a crucial role in this initialization process. It ensures that the initial water level is consistent with the specified inlet conditions and the gravitational forces acting on the fluid. This consistency is essential for preventing spurious pressure waves or unrealistic water surface elevations from developing during the initial stages of the simulation. Think of this initialization process as setting the stage for our virtual experiment. We carefully position the boat hull in its starting location, ensure the water surface is calm and level, and set the initial flow conditions. Once these initial conditions are established, we can release the virtual boat and observe how it interacts with the surrounding water, guided by the physical models and boundary conditions we have carefully defined. This initialization step, while often overlooked, is a crucial aspect of setting up a successful CFD simulation. A well-defined initial state provides a stable foundation for the solver to build upon, increasing the likelihood of achieving a converged and physically realistic solution. It's like ensuring a fair start in a race, allowing the true dynamics of the system to unfold without any artificial biases. The balancing act, achieving simulation stability. Running a transient CFD simulation, especially one involving dynamic mesh movement like our planing boat hull, is akin to navigating a ship through turbulent waters. It requires a deft hand at the helm, constantly adjusting course and speed to avoid treacherous currents and maintain a steady course towards a stable and accurate solution. Instabilities like rogue waves can arise unexpectedly, threatening to capsize our simulation and send our virtual experiment off course. Several factors can contribute to instability in transient simulations. The strong coupling between the boat's motion and the surrounding fluid flow is a prime culprit. As the hull moves, it generates pressure waves and displaces water, altering the flow field, which in turn influences the forces acting on the hull. This intricate interplay, while fascinating from a physics standpoint, can lead to numerical oscillations and instabilities if not handled carefully. The choice of numerical schemes and parameters also plays a crucial role in maintaining stability. Large time steps, while tempting for reducing computational cost, can overshoot important flow features and lead to divergence. Inadequate convergence criteria within each time step can allow errors to accumulate, gradually steering the solution away from physical reality. Even the boat's initial position and the initial flow field can influence stability. Starting the simulation with the boat too far from its equilibrium planing state or with an unrealistic initial flow field can introduce large transients that the solver struggles to handle, increasing the likelihood of instability. Solution stabilization, a helping hand for convergence. To tame the turbulent waters of our transient simulation and guide our virtual boat towards a stable planing state, we employ a powerful tool solution stabilization. Think of this technique as a stabilizing gyroscope for our simulation, counteracting disruptive forces and promoting a smoother, more controlled convergence towards a physically realistic solution. ANSYS Fluent offers a range of solution stabilization methods, each designed to address specific types of instabilities. For our planing boat hull simulation, we opt for a technique known as coefficient-based stabilization. This method subtly modifies the pressure update equation at each iteration of the solver, enhancing stability without compromising the accuracy of the final converged solution. Imagine this coefficient-based stabilization as a gentle hand guiding our simulation, subtly adjusting the pressure field to prevent oscillations from spiraling out of control. It acts primarily near moving boundaries, such as the hull surface, where the interplay between fluid flow and mesh movement is most pronounced, and the risk of instability is highest. The key parameter controlling the strength of this stabilization is the stabilization coefficient, typically set between 0 and 1. A higher coefficient provides stronger stabilization, but can also slow down convergence. For our simulation, we find that a value of 0.2 strikes a good balance between stability and efficiency. It's important to note that solution stabilization is not a magic bullet. It's a tool that, when used judiciously, can significantly enhance the stability and robustness of our simulation. It's essential to monitor the simulation closely, even with stabilization enabled, adjusting parameters and schemes as needed to ensure that the solution remains physically meaningful and that we haven't inadvertently suppressed any important flow features. Quantifying performance, drag, trim, and sinkage. After the hum of the computer processing our simulation subsides, we're left with a treasure trove of data ready to be mined for insights into our boat hull's performance. But, raw data alone won't reveal the secrets of our virtual test. We need to process, analyze, and interpret this data, transforming it into meaningful metrics that quantify how our hull behaves in the virtual water. Our first target is drag, the nemesis of any vessel striving for speed and efficiency. ANSYS Fluent diligently tracks the drag force acting on the hull throughout the simulation, allowing us to plot its evolution over time. Initially, drag is high as the hull, still mostly submerged, pushes through the water. As the boat accelerates and the hull begins to plane, the drag force gradually decreases, eventually reaching a relatively stable value. This stabilized drag value, often referred to as the planing drag, is a crucial performance indicator. A lower planing drag translates to higher speeds for a given engine power or improved fuel efficiency at a constant speed. By comparing the planing drag of different hull designs or operating conditions, we can quantify the impact of these changes on performance and guide our design optimization efforts. Trim angle, our second metric of interest, is another key indicator of hull performance. As the boat transitions from displacement to planing, the bow lifts out of the water, resulting in a positive trim angle, the angle between the hull's keel line and the horizontal water surface. This trim angle influences both drag and stability, and finding the optimal trim angle for a given hull design and speed is crucial for maximizing performance. ANSYS Fluent allows us to extract the boat's orientation at each time step, enabling us to calculate and plot the trim angle over time. By observing how the trim angle evolves, we can assess how quickly and smoothly the boat transitions to planing and whether it exhibits any undesirable oscillations or instabilities. We can also correlate the trim angle with the drag force, identifying the trim angle that minimizes drag for a given speed. Finally, we turn our attention to sinkage, the vertical displacement of the hull into the water. Excessive sinkage increases wetted surface area, leading to higher drag. By monitoring the vertical position of a reference point on the hull, typically the keel, we can quantify sinkage and analyze how it changes with speed and trim angle. This information is particularly valuable for understanding how hull design modifications affect the boat's draft and its ability to maintain a favorable running attitude at high speeds. Visualizing the flow insights from images and animations. While quantitative metrics like drag, trim, and sinkage provide valuable insights into hull performance, they only tell part of the story. To truly understand the complex interplay between the hull and the surrounding water, we need to visualize the flow field to see the invisible forces at play and gain an intuitive understanding of how our hull design influences the fluid dynamics. ANSYS. Fluent offers a rich palette of visualization tools to bring our simulation results to life. We can generate static images, like snapshots frozen in time, capturing the flow field at key moments during the simulation. These snapshots, often color-coded to represent pressure, velocity, or turbulence intensity, allow us to pinpoint areas of high-pressure drag, flow separation, or vortex formation. But the true magic of CFD visualization lies in animations, moving pictures that breathe life into our data, revealing the dynamic dance between the hull and the water. Imagine watching a high-speed video of our virtual boat slicing through the water, leaving a trail of waves in its wake. Animations allow us to observe how the flow field evolves over time, how the hull generates waves, and how these waves, in turn, influence the forces acting on the boat. We can visualize the water surface itself, watching as it deforms under the hull's influence, forming a dynamic wave pattern that propagates outward. We can track the movement of individual particles within the flow, revealing intricate flow patterns and recirculation zones. We can even visualize the pressure distribution on the hull surface, watching how it changes as the boat accelerates and the trim angle changes. These visualizations are not merely aesthetically pleasing, they are powerful diagnostic tools that allow us to understand the complex flow phenomena affecting hull performance. By carefully studying these visualizations, we can identify areas of high drag, optimize hull shape for reduced wave-making resistance, and ultimately design more efficient and higher-performing planing boat hulls. From simulation to success mastering planning hull design, this comprehensive guide has taken you on a journey into the heart of planing boat hull simulation using ANSYS Fluent. We've explored the fundamental principles, the intricate setup, the delicate balance of achieving stability, and the art of extracting meaningful insights from the sea of data. Mastering these tools and techniques empowers naval architects and marine engineers to elevate hull designs from sketches on paper to meticulously optimized high-performance vessels. The ability to accurately predict drag, trim, and sinkage, the holy trinity of planing hull performance, is nothing short of transformative. No longer are we confined to expensive and time-consuming trial and error approaches in the physical world. CFD simulation provides a virtual proving ground, allowing us to test countless design iterations, explore a wide range of operating conditions, and pinpoint optimal configurations before a single drop of water meets a physical hull. This shift from physical to virtual testing not only accelerates the design process, but also unlocks a level of understanding that was previously unattainable. We can visualize the invisible, peering into the complex flow patterns around the hull, identifying areas of high drag, and understanding how subtle design changes ripple through the fluid dynamics. This knowledge is power, the power to design hulls that slip through the water with minimal resistance, that maintain a stable and efficient running attitude, and that ultimately deliver exhilarating performance on the water. The mastery of planing boat hull simulation is a testament to the power of human ingenuity, harnessing the tools of computational fluid dynamics to push the boundaries of what's possible in marine design. Charting the course ahead, expanding the simulation horizon. While this guide has provided a solid foundation for simulating planing boat hulls, the world of CFD is vast and ever-evolving. The techniques we've explored are but stepping stones on a journey of continuous learning and exploration, leading to ever more sophisticated and insightful simulations. One path forward lies in refining our meshing strategies. Mesh sensitivity studies, where we systematically vary the mesh density and assess its impact on the results, allow us to find the sweet spot between accuracy and computational cost. Adaptive mesh refinement techniques, where the mesh dynamically adapts during the simulation to concentrate cells in regions of high flow gradients, offer further potential for enhancing accuracy without overburdening our computers. Exploring alternative turbulence models is another avenue for advancement. While the K-Omega SST model served us well, a plethora of other models exist, each with its own strengths and weaknesses depending on the specific flow characteristics being simulated. Comparing results obtained with different turbulence models can provide valuable insights into the sensitivity of our predictions to this crucial aspect of fluid behavior. Venturing beyond the idealized world of calm water simulations opens up a realm of exciting possibilities. Simulating the interaction of our planing hull with waves, both regular and irregular, allows us to assess seakeeping performance, a crucial aspect of real-world boat design. This involves modeling the complex dynamics of waves interacting with the moving hull, a challenging but rewarding endeavor that can lead to safer and more comfortable vessels. Further down the line lies the realm of multi-phase flow simulations, where we can incorporate the effects of cavitation, the formation of vapor bubbles in regions of low pressure, or even model the interaction of the hull with a spray of water droplets. These advanced simulations, while computationally demanding, hold the potential to unlock even deeper insights into the intricacies of planing hull performance. As computational power continues to increase and our understanding of CFD techniques deepens, the possibilities for simulating planing boat hulls, and indeed any fluid structure interaction problem, are limitless. The journey we've embarked upon in this guide is just the beginning, a launching pad for future explorations that will undoubtedly lead to even more innovative, efficient, and awe-inspiring vessel designs.